Okay, today's problem looks at the problem of a ball which is falling with free fall. The function f of t describes the distance the ball has fallen over time in seconds. F of t is equal to 4.9 t squared. We have a graph drawn here. We can see that the ball will start off at no distance having travelled, will travel further and further away, and we can also see that as the curve slopes up that it's going to be accelerating and getting faster. Our problem is to find the velocity of the ball when t is equal to 1. There's going to be a few different ways to do this. We have a secant line drawn here. We can calculate the value of the distance that it's travelled at this point. We can calculate how far it's travelled at 2 seconds and then calculate it. So, the velocity is going to be equal to the derivative of the function. We denote the derivative with this symbol here when t is equal to 1. We can make an approximation of that using a secant line and the change quotient. We need the change in f of t over the change in t. We can calculate this with f of 2 minus f of 1, and this will give us the change in distance, the y-coordinate here, minus the y-coordinate here. The change in time is from 2 seconds to 1 second, so 2 minus 1. We can use our calculator to do this. So let's bring in the calculator, enter in the function 4.9x, 4.9x squared, enter. Then we need to make press variables, scroll across to y variables, choose function, y1, and enter in 2 seconds. From this we shall subtract, same again, y1, and enter in 1 second. Divide this by 2 minus 1. Got a little bit of a mistake there. Scroll backwards through it before I enter it. Press divide and enter. And we get 14.7. That's going to have some kind of units. The units of the distance is in meters. The units of the time is in seconds. So meters divided by seconds gives us meters per second. Now, that's not very accurate. How can we make it more accurate? Well, obviously the ball is going to be travelling a lot faster here than it is at this point. And we're calculating the average speed over this period, around about this point. We can simply make this point move a lot closer, and then we're calculating average speed around about 1 second. And that's what we'll do next. We can make a more accurate estimate of the speed using the same formula, the change in distance over the change in time. But instead of putting our secant line so far apart, we can put it quite close together. We have the algebraic formula which allows us to do this. So we can put it at 1.01. Becomes a lot closer. Our distance now over the bottom is 1.01 minus 1. Using the calculator again, we can just press second entry, scroll through this, changing that 2 to a 1.01. We're going to have to press insert so it overwrites 1.01, and then we scroll through to this point and insert 0.01. Just checking it through. Yep, we're good. Let's enter this, and we get a much closer estimate. How can we make it more accurate still? How can we make it more accurate still? This isn't quite right. Well, we just need to keep moving this closer and closer. Ideally, we want this to equal 1. The problem is, if this equals 1, and this equals 1, so do these two. And if these two equal 1, then their difference is 0. And we divide by 0, and this can't happen. So we use... Okay, so if the difference can't be equal to 0, it needs to at least approach 0. This is where the derivative comes in. We have our definition of the derivative as a function. We let the difference between the x values approach 0 using limits. So the derivative is the limit of this h approaches 0 of f of x plus h minus f of x all over h. To use it in this example, we have our definition. To use it in this example, we're going to need to find f dash of 1. That's the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. We can use the function here to make these calculations. What we're going to get is 4.9 times 1 squared plus 2 times 1 times h plus h squared minus 4.9 times 1 squared all over h. If we expand the bracket, we're going to get 4.9 plus 9.8 h plus 4.9 h squared minus 4.9 all over h. We need to make some simplifications. We have a plus 4.9 here and a minus 4.9 here. We have an h here, an h here, and an h squared here, so we can remove that. Our simplification is going to be the limit as h approaches 0 of 9.8 plus 4.9 h. Now if we let h approach 0, this term will also approach 0, giving us a result of 9.8 meters per second, which, as you should recognize, is acceleration due to gravity.